Welcome. There's a gap between code that compiles and code that's actually good C++. This lesson is about closing that gap. We're covering the standard template library, specifically containers, iterators, and algorithms. Instead of writing manual loops for everything, you'll learn to express operations like searching, counting, transforming, and sorting using standard algorithms. The result is code that's shorter, clearer, and less error-prone. Let's get started. You already know vector from earlier lessons. Now, let's pair it with algorithms. We create a vector of integers, 5, 2, 8, 1. Then we call std sort, passing begin and end iterators. After the call, the vector is sorted, 1, 2, 5, 8. Iterators are the bridge between containers and algorithms. Begin points to the first element. End points one past the last. Every standard algorithm works with this iterator pair pattern, and vector remains the default container, contiguous memory, cache-friendly, and compatible with every algorithm in the library. Two of the most common algorithms, find and count. Find returns an iterator to the first element that matches. If no match exists, it returns end. Count returns how many elements match. For conditions beyond simple equality, use the if variance. Countif takes a predicate, a lambda or function that returns true or false. In this example, we count how many values are 50 or above. The predicate is a lambda, takes an int, returns whether it's greater than or equal to 50. Findif and countif are often the first algorithms you reach for when the condition isn't a simple value comparison. Transform applies a function to every element and writes the results to an output range. We create a destination vector called doubled, pre-sized to match the input. Then we call std transform with the input range, the output beginning, and a lambda that multiplies by 2. Every element is doubled. The key insight? You describe what the transformation is, not how to loop through the elements. The algorithm handles the iteration. This pattern is clearer than a manual for loop because the intent, transform every element, is explicit in the function name. Here's the main lesson of this chapter. Stop thinking about loops and indices. Start thinking about operations on ranges. Need to find something? Use find or find if. Need to count? Use count or count if. Need to transform every element? Use transform. Need to sort? Use sort. Each algorithm expresses a specific intent. When you read std sort, you know exactly what's happening. When you read a 20-line for loop, you have to trace the logic to understand the same thing. Algorithms are self-documenting. They reduce bugs by eliminating off-by-one errors, boundary mistakes, and forgotten edge cases. A realistic pattern. Select a subset, then compute something over it. We have exam scores: 91, 84, 76, 99, 88. First, we use copy if to select passing scores, those 80 and above, into a new vector. The backinserter adapter grows the destination vector automatically as elements are added. Then we use accumulate to sum the passing scores. Two algorithm calls replace what would typically be a loop with a conditional and a running total. The code reads like a description of the operation. Copy the scores that pass, then sum them. Here's a classic gotcha. The std remove algorithm doesn't actually remove elements from a container. It rearranges the elements so the ones to keep are at the front, and returns an iterator to the new logical end. The leftover elements at the back are still there. You need to call erase on the container to actually shrink it. The classic pattern: values.erase, then std remove with begin, end, and the value to remove, then values.end. This two-step dance is called the erase-remove idiom. In C++20, there's a simpler alternative: std erase of values, 0. One call, direct intent. Prefer this modern form when your compiler supports it. C++20 introduced the ranges namespace, and it simplifies algorithm calls significantly. Instead of std sort with begin and end, you write std ranges sort of values. Instead of std find with begin and end and the target, you write std ranges find of values, 8. No more begin-end boilerplate. The ranges versions work directly with containers. They also support projections, which we'll see next. If your compiler supports C++20, prefer the ranges overloads. They're shorter, harder to misuse, and more expressive. Real programs don't sort plain integers. They sort objects. Here we have a user struct with a name and a score. We want to sort users by score in descending order. With ranges, this is one line. std ranges, sort of users, std greater, ampersand, user score. The third argument is a projection. It tells the algorithm which member to sort by. No need to write a custom comparator lambda. Projections work with sort, find, countif, min element, max element, and many other range algorithms. They're one of the most useful features of the ranges library for working with structured data. 5 algorithms worth learning next. Findif returns an iterator to the first element, matching a predicate. Essential for searching by condition. Partition rearranges elements so everything matching a condition comes first. Useful for grouping before processing. Accumulate combines a range into a single result using an operation. Sums, products, string concatenation all work with accumulate. All of, any of, none of. 3 Boolean algorithms that express checks directly. All of returns true if every element matches. Any of returns true if at least one matches. None of returns true if 0 match. And rotate shifts elements left or right without the index juggling you'd need in a manual loop. 3 mistakes to watch for. First, forgetting that remove doesn't erase. If you call std remove and don't follow it with erase, the container still has the same size. The removed elements are just shuffled to the back. Second, using algorithms that require sorted input on unsorted data. Binary search, lower bound, upper bound, and equal range all assume the input is sorted. Using them on unsorted data gives meaningless results with no compiler warning. Third, writing manual loops where an algorithm would be clearer. If your loop is just finding, counting, transforming, or sorting, there's an algorithm for that. Use it. Here's the practical rule of thumb. If the loop is about searching, filtering, transforming, or checking a condition, look for a standard algorithm first. Algorithms are tested, optimized, and self-documenting. But if the loop maintains complex invariants across several moving parts, multiple state variables, interleaved conditions, non-trivial control flow, a normal loop may still be clearer. Not every loop should be an algorithm call. Use judgment. For next topics, continue with templates and generic code to learn how to write functions and classes that work with any type. Then, error handling for exceptions, error codes, and expected. You now have the STL toolkit. Use it. Thank you.